So when we're talking about endothermic and exothermic reactions, if we look at a reaction like this, what we're doing is we're going to break existing bonds, okay, and allow them to be separate before we form the new bonds of the products. So all of the reactants within our chemical reaction, all of our reactants, they get separated. So over here, the hydrogens, H2, those molecules get separated from one another. Because technically speaking, on this side, we have two H2s like this, okay? And they join together. On this side, we have one O2, and that O2 is joined together like this, okay? What we need to do across the arrow, is we make sure that each of those things are separated. I just want to change the color of the oxygens so that you have an idea of what I'm talking about. So here, okay, that's effectively what the middle of the reaction looks like. It means that we've taken all the reactants and we've separated them, the individuals, before we actually form our products. Because now, all of these individuals can find new partners. Makes sense? Okay? This is referred to as an activated complex. Okay? An activated complex. Now, it takes a certain amount of energy to break these existing bonds. So it takes energy to split things. And when new things are formed, when they bond, energy is released. Okay? Yes? Now there is a value attached to how much energy it takes to break certain bonds. So in a hydrogen to hydrogen bond, it always takes the same amount of energy to break hydrogen to hydrogen bonds. Okay? So when they get pulled apart, it takes a certain amount of energy. But what's awesome is that if you were to form an H2 molecule, that same amount of energy would be released. So it's very in balance. The amount of energy it takes to break the bond is the same amount of energy that would be given off if that bond were formed. Yeah? You do not need to know those bond energies off by heart. So you don't need to memorize how much it takes. You will usually be given a table that tells you. So I'll refer you to your textbook where the table is for our reference. Okay? The energy that is supplied to you, the values that are supplied in the table, are very approximate. Do you understand what I mean by that? So they're very approximate in that some sources will give you slightly different values to others. So you'll notice that I am using certain values in my PowerPoint, but they might be a little bit different from your textbook. Okay, because they're just approximate values. So let's start by talking about some of the definitions related to our particular section right now. When we're talking about energy and change, okay, one of the first things we need to talk about is, when we talk about this, we're going to be looking at breaking and forming of bonds. We're going to be talking about the application of exo and endothermic. We're going to talk about bond energy, and then we're going to talk about activation energy, activated complexes, and we're going to talk about energy profiles and catalysts. Now, you can start making notes if you'd like, but I am going to post this pretty much now on Google Classroom so that you can, it might be easier to follow when you're at home to create the notes. Okay, because I want to go through it quite quickly. Are we okay with that? Are you sure? Okay. So, the first definition that I'd like you to have is that an exothermic reaction is a reaction that releases heat or energy. Heat flows from the system to the surroundings. So energy is released to the surroundings. This is a really big definition, okay? Energy is released to the surroundings, and what that usually means is that if we had a reaction happening in a container, the container will get hot, okay? Now, a prime example of this is a reaction of acid and water. If I add acid to water, the container immediately becomes warm. I think I've done this with you, where it's quite dramatic how hot the actual beaker gets because the reaction is so violently exothermic, which is really, really cool. Okay? Next week, I'll bring down some stuff so that we can actually play with what's really, really happening during this. Okay, we'll look at it in terms of thermometers and all sorts of things. So heat is given to the surroundings. I need to ask you a question. What do you think the surroundings are when we talk about this?
The environment around it.
The
Environment around it.
Can you be specific? Let's say we're dealing with an acid and water. What would be the surroundings?
The container.
The container, but more specifically, actually, it's the water molecules that are not involved in the reaction. Those water molecules that are not involved in the reaction, they will be the ones that absorb the energy first. Okay? Once they've absorbed the energy, they then make the side of the container hot. Okay? Yes? So, that is our definition for an exothermic reaction. So heat flows to the surroundings. Have you got that? It's okay if you don't have it, like I said. Just try, and then what we'll do is we'll
Should I pause it?
no, it's fine.
Okay.
It's a very real, very real lesson for those following from home, which is cool. All right, guys. An endothermic reaction is our next definition. Now, an endothermic reaction is the reverse. It's a reaction during which the energy is absorbed. Okay, so energy gets absorbed. The overall energy gets absorbed. So heat flows from the surroundings into the system. And what actually ends up happening is that your surroundings lose energy, which means, remember, temperature is simply a measure of the average kinetic energy of the particles, yes? Do you remember that? Temperature being a measure of the average kinetic energy of the particles. So what's happening is that in an endothermic reaction, heat flows from the surroundings into the system. In other words, it's absorbed into the actual bits, and that means that the surroundings decrease in temperature. So if we did this with a lot of soluble salts, okay, like ammonium chloride, when you mix it with water, they are endothermic reactions. So the beaker would get cold because energy is being absorbed from the surroundings, which means the beaker will get cooler. Does that make sense? Next week we will play with that so that you can actually feel the fact that energy gets absorbed by the system. Okay? Now, when we talk about endothermic and exothermic reactions, what we need to realize is the bit that I've got on the board still is happening during these reactions. So right at the beginning I said that energy here is released, energy here is absorbed. Right? What defines this or makes this an endothermic or exothermic reaction relies on the balance between these two things happening. So if a reaction ends up releasing more than it absorbs, then it's an exothermic reaction. If it ends up absorbing more than gets released at the end, it ends up being an endothermic reaction. Do you see that? So during an endo or an exothermic reaction, the process of absorbing and releasing, both things happen. It's just about what the overall effect is that counts. Does that kind of make sense? So one more time. If the reaction absorbs more than it releases, it's an endothermic. If it releases more than it absorbs, it's then an exothermic. Yes, Sean. Then the reaction doesn't have any change in the temperature, and we can't define it as either endo or exo. All right. Chloe, will you pause for us for a second? Okay. So the concept of enthalpy is exactly what we were talking about before. It's that balance between energy absorbed and energy released. So enthalpy relates to the total amount of chemical potential energy in a chemical system. Okay. Enthalpy is therefore that balance, and it can be calculated. Right. So let's look at the next concept. Let's look at the next concept. Are you ready for it, guys? Just about? Enthalpy. Right.
Enthalpy.
So, we say that delta H, enthalpy, is equal to the energy of the products minus the energy of the reactants. Okay? So in other words, we're looking for the change. Remember, change is always final minus initial. That's why it's products minus reactants. Okay? If we get an endothermic reaction, then that means that delta H is greater than 0. I always get confused between the crocodile thing. Do you know what I mean? The greater than, and I always get confused. You don't.
I still get
Oh, you're okay. You're not okay as well. All right. So when I talk about this, there are two ways that we can describe an endothermic reaction. We can say that an endothermic reaction is going to have our delta H, all right, being greater than 0. So the change is greater than 0, which means that delta H will have a positive value. All right? Delta H will have a positive value. That makes sense? Yes? What it means is that the change in the energy is positive. And what that means is that more energy is absorbed than was released, because you end up with more energy at the end. Yes? If you compare start to finish, all right, and you have more energy at the end, you're going to get a positive value because it's final minus initial. So if final is bigger than initial, you're going to get a positive value, which means that the system has pulled more energy in than it had initially, which is why you get a positive answer. Does that make sense? Are you sure? Right. By the same token, it means that an exothermic reaction, the reactants versus the products are going to be lower than the reactants, okay? Because energy has been lost. It's given more energy to the surroundings, yes? So in an exothermic reaction, we're going to have delta H having a negative value. The change in energy will be negative because what we have initially is more than what we have finally, because we've lost energy, okay? And so delta H will have a negative value. Those two concepts are so important. Okay, so just get those down. All right. Now, let us look at what happens. So when we're breaking and forming of bonds during a chemical reaction, existing bonds in the reactants are broken and new bonds are formed to create products. So I thought I'd give you a sentence so that you can hang on to that sentence, because sometimes we get a little bit confused, right? So the sentence that says during the reaction, existing bonds in the reaction or in the reactants, let me just move that over. In the reactants are broken and the new bonds are formed to create products. All right. So products are created. If I give this to you visually, that means that here, when the existing bonds are broken, the energy is absorbed, and then over here, when the new bonds are formed, the energy is released. Okay? So, let's look at how we can do this mathematically. That's what we're going to look at now. I will go back and give you a chance to just if you just leave the space, I'll go back and just give you a chance to take that down once we get to a point. Okay, sorry guys, I'm going to move on. Bond energy is the energy absorbed. If you guys can stop writing now, we'll just talk our way through the rest and then I'll go back, okay? So bond energy is the energy absorbed when the bonds break, or the energy that is released when a new bond forms. That is referred to as the bond energy, okay? So energy change, which is delta H, talks about the sum of the energy absorbed minus the sum of the energy that is released, the forming bonds, okay? And then I'm going to do some examples. So we're going to pause there.